Today we will talk about the fault tolerant operation of cascaded edge bridge converter. So, one of the very important feature of a cascaded edge bridge converter is its fault tolerant feature. What do you mean by fault tolerant? Now, there can be several types of faults in a converter. The fault may be, for example, in the device, the fault can be in the gate driver circuit, the fault can be in the interconnection of two cells. For example, here there are two cells and there is a fault or there is a disconnection of the wire which is connecting two cells. There can be other types of faults. For example, you can have fault outside the converter, like you can have a fault on the cable which is taking the power from the converter to the motor. There can be non-electrical faults. For example, you can have a thermal overtrip. So, one of the converter component is heating up to temperature which is more than the permissible limit. There can be mechanical faults also, some part may be broken due to vibrations. So, there may be several types of faults. Now, we are here mostly concerned with the electrical faults. Now, electrical faults can again happen in a number of places. We are again focusing more on the converter, the faults inside the converter. Now, fault inside the converter can or most likely to happen inside one cell. Okay. So, inside the cell one IGBT may be damaged, that is one fault. The capacitor may be damaged, the DC bus capacitor. Here inside the cell you have rectifiers, you have capacitors and you have transistor or IGBTs. So, again capacitors, in particular these type of electrolytic capacitors are very prone to failures. Okay. In fact, they are the one of the least reliable component in a power electronic converter. So, there can be several types of faults. Now, often this type of fault, and remember this is a big converter and there are many components, there are many cells, and inside each cell there are many components like that. So, often it these type of converters are used in mission critical applications. What do you mean by mission critical application? Say one of the applications for such cascaded edge bridge converter is for motor drive applications, and where do we use these motor drives? For example, for running pumps, and these pumps are used for extracting oil from the mines. Okay. This is one of the applications. So, these kind of converters are used in the oil and gas industry. There are many other places where these kind of converters are used, where the continuity of service is essential. I mean because there are many components in this converter, and since there are many components, each component has a probability of failure, and so the chances of failure is quite high in this kind of a converter. But you do not want the whole converter to shut down because of failure inside one single component inside one cell. Okay. For example, the gate driver board in one cell, one gate driver board for one IGBT inside one cell, there can be a small fault in that gate driver board, and because of that, if you say that okay, we will shut down the whole converter because of that single fault, then it defeats the purpose, because you have so many components, and because of a single fault in one single component inside the converter, you are basically shutting down the whole converter, and this may not be acceptable for many mission critical applications, because if you shut down the converter, of course, then the motor shuts down and then the pump also shuts down, and the whole process will be disrupted, and the cost of downtime or the cost of shutting down the whole process in terms of money can be enormous. So, we do not want the whole process or the whole converter to shut down because of a single failure inside one converter. So, we have to think of developing some kind of a fault tolerant feature inside this converter. In fact, this cascaded edge bridge converter has an inherent fault tolerant feature, which we will discuss today. So, the idea here is that if you have a fault inside one cell, then you can bypass that cell and can still continue to operate the converter, but with a reduced rating. Okay. So, this is the idea, that you have a fault inside one cell, you bypass that faulty cell, but still continue to run the converter with the remaining healthy cells. Of course, some compromise regarding the rating of the converter has to be done. Once this is done, when the faulty cells has been bypassed, then at the next scheduled maintenance you can take out that faulty cell and then can repair it and again insert it back, or you can, if the fault cell is faulty to the extent that you cannot repair it, then it is possible to insert a new cell. So, what do we gain from this is that at least the service is continued. Okay. You can run the motor, but for example, you can run the motor, but maybe at a slightly reduced voltage and a slightly reduced power, but at least some production, the whole production is not stopped because of a failure in or a single point failure in the converter. Now, our discussion today is to have a glimpse of how can we achieve this in this cascaded edge bridge converter. If you look into the cell structure of the converter, then you can see that each cell, we have discussed it earlier, we have shown it, each cell has a rectifier and you have a capacitor and then there are transistors. What we did not show earlier was that each cell output has a bypass switch arrangement. Okay. So, you can see here there is a bypass switch arrangement. The bypass switch arrangement is used to bypass the cell in the event of a fault. Okay. So, it consists of there are two parts in this bypass switch, and one part is an electronic switch, which is, you can see here, is a back to back thyristor or a triac arrangement, and there is a mechanical switch. Okay. So, the bypass switch consists of two parts, an electronic switch and a mechanical switch. So, suppose we turn on the mechanical switch, then this whole cell is completely bypassed. Of course, when we do that, we also turn off the IGBTs, or we also turn off the transistors inside the cell, so that the whole cell is completely bypassed, but the converter can still continue to operate. Now, why there are two switches? So, if you see here a little bit this diagram of a cell, you can see that there are two switches, one is an electronic switch and one is a mechanical switch. Now, electronic switches are faster. Okay. Electronic switches made of semiconductors, for example, the triac here, the back to back thyristor, this is faster, okay, as compared to the mechanical switch. So, when a fault is detected, at first this back to back thyristor or the triac is fired, and within tens of microseconds then this thyristor starts to conduct. So, the current will be bypassed. So, at first the transistor is switched off. So, if you detect that there is a fault, severe fault inside one cell, then you can first switch off the transistors and then you can fire the thyristors or the triacs. But since this is a semiconductor, it has some on state loss, which we would ideally do not want, because this is a bypass cell and we do not want additional losses to happen. So, eventually we will bypass the whole circuit with a mechanical switch, typically a circuit breaker, which operates in the range of hundreds less than 100 milliseconds, say 3 to 4 cycles, maybe 60 to 80 milliseconds it will take. So, after this 100 millisecond, then a mechanical switch fully isolates this cell, and then the cell is, for example, outside the circuit, and probably with some necessary precautions it can be taken out of the converter with during a scheduled maintenance operation. The mechanical switch takes more time, say in the order of 100 millisecond, close to 100 millisecond, and that is why the electronic switch, there are two switches, one is a fast switch and one is a slow switch. The fast switch is the triac, while the slow switch is the mechanical switch. And there is also on this, each of these cells have a local controller, and this local controller basically gets its power from the DC link of the converter of the cell. From this DC link, this local controller is powered, and it communicates with the main controller, which runs the whole converter, and it communicates through fiber optic signals. So, that necessary electrical isolation is maintained. The local controller has several sensing circuits. For example, it can sense the current flowing through the terminal out. It can also sense, the gate driver board can also sense the VCE, the collector emitter voltage of the transistor, and by checking the saturation voltage VCE, it is possible to identify that whether, for example, an IGBT is short circuited. Normally the VCE sat or the saturation voltage of the IGBT is around 1.7 volt, but it will drastically increase 2.5 to 3 volt when there is a fault or when the high current passing through the transistor or IGBT. We can sense that VCE sat voltage and can detect there is a short circuit in the IGBT, and the local controller can take a quick decision that shut off the pulses to the IGBT. At a later point of time, if there is a severe fault, say in the cell, then it is possible for the main controller to also bypass the whole cell with the help of the bypass switch arrangement. So, once we have bypass of the cell, then we do not have those cells available. So, they are completely bypassed from the circuit. Now, how does the circuit look like when there is a bypass? So, on the left hand side, we have shown a cascaded edge bridge converter with 5 cells in each leg or in each phase. So, you can see here cell A1 to A5 here, 5 cells. Now, this is a healthy converter. Since there are 5 cells in each phase. So, we denote this combination as 5 5 5 here, 5 in A phase, 5 in B phase and 5 cells in C phase. Okay. And all of them are perfectly healthy, and so all of them are in the circuit. Now, suppose we have a fault condition and there may be kind of like several faults over time. Okay. And in such a case, we are taking a general case here, and suppose the faulty condition is denoted by 543. What does 543 mean? 543 means that there are 5 cells in A phase, 4 healthy cells in B phase and 3 healthy cells in C phase. Okay. And this is diagrammatically shown in this picture. You have 5 cells in A phase, 4 cells in B phase, that is cell B5 is faulty and has been bypassed. Okay. And in C phase we have 3 cells working and 2 cells bypassed, they are faulty and have been bypassed. So, a faulty condition in this converter is denoted by this 543 combination. Okay. Now, when there was all cells were working and all of them were healthy, that is this 555 combination, how does the pole voltage and phase voltage look like? That is shown by this triangle here. The voltages are all balanced during 555 condition. So, the AO, BO and CO, that is AO means the pole voltages, this point is A here. So, this is the A, B and C, and there is a neutral point of the motor. So, the motor if it is star connected, there is a neutral point here in. So, the AO, BO and CO voltages are equal in magnitude and they are 120 degree phase apart. So, the line voltages AB, BC and CA are equal and 120 degree apart in time, and so we get an equilateral triangle because it is a balanced system. Okay. And the converter neutral, that is this point O, the potential at point O and the potential at point N, they are same. Okay. So, O and N points are coinciding with each other during this condition of 555 with the cascaded edge bridge converter. Now, what happens when there is a fault? Suppose we take this 543 combination. Now, of course, we understand that the pole voltages VAO, VBO, VCO are no longer balanced. Okay. We cannot produce the same voltage magnitude from A phase, B phase and C phase any further. Of course, you can argue that if we increase the voltage on the DC bus of the cells, of course, you can do that. You can increase the DC bus of say, if you increase, you can increase the DC bus of cells in phase B. Okay. In this case, you have lost one cell. So, if you increase the DC bus of each cell of phase B by 20%, you can get the same voltage from 4 cells. But this is not a good practice because of simply because of the reason that all these cells are designed for a specific voltage. So, for example, suppose let us take an example, if this DC bus of the voltage is designed to be 1000 volts, then you may choose an IGBT of 1700 volt rating. Okay, voltage rating of the IGBT can be taken as 1700 volt, keeping a safety factor of 1.7. Now, why this 1.7? Because there may be several reasons why the designer can keep 1.7 as the safety factor. For example, why 1.7 has been, or why someone takes 1.7 as the safety factor. Say for example, 1000 volt is on the DC bus. The first thing is, this 1000 volt is not a constant value, it will have a ripple, and under some circumstances it may be possible that there is a regenerative operation from the motor, where the motor is acting as a generator and pumping back energy into the DC bus. Now, on the input of the DC bus is a diode rectifier, so it cannot take the energy back into the supply. So, whatever is the energy coming from the motor will be again dumped into the capacitor, the DC bus of the capacitor. So, its voltage, which is normally designed at 1000 volt, will increase, say it may increase to 1200 volts. So, a regenerative operation can take place. During that point of time, the IGBTs have to withstand this voltage. Secondly, when there is a switching happening in this IGBTs, there is always a voltage overshoot on the terminals, always, unless you, I mean, it is a matter of how you design the gate driver board, but there will always be a voltage overshoot at the collector emitter terminals, and this voltage overshoot can easily be 15 to 20% under some circumstances. So, we have to keep a certain margin for that. So, there may be several such considerations which must be kept for deciding this safety factor. Okay. So, if the nominal voltage of the DC bus is 1000 volt, a transistor of 1700 volt may be taken, or a transistor or a IGBT of 2300 volt may be taken. Compromising on this safety factor is actually not a good idea. Okay. So, we must keep this safety factor, otherwise if you increase the DC bus of these cells, then it may happen that you lose all the cells, because you have compromised on the safety factor, voltage safety factor. Then you can, over a quick time, you may lose all the cells. So, that you do not want. So, you do not want to compromise on the safety factor which has been kept there by design. So, increasing the DC bus voltage on these cells is not a good option. So, now, so if you have a cell, if you have a bypass of this cell B5 and you have a bypass of cells in C4 and C5, then the pole voltages will automatically get unbalanced. Okay. Now, there is also another option which is possible. The option is that in order to get balanced voltage, there is one more option possible, that you also suppose you have lost two cells in C4 and C5, then what you can do in order to get balanced voltage is that you can also bypass two healthy cells in phase A and one healthy cell in phase B. For example, in order to get balanced voltage, you have lost two cells in C4 and C5 and you have three healthy cells in C phase here. What you can do is, you can say, okay, fine, in order to get balanced voltage, I will only operate 3 healthy cells in B phase and 3 healthy cells in A phase, that is a possibility, and I get a balanced voltage. That is definitely a possibility, but what we will see in the analysis is that the magnitude of voltage that is obtained by this process will be less as compared to the case where we use all the available healthy cells. So, if we bypass some of the healthy cells, then actually we are losing on the voltage. Okay. So, that is not a very I mean bypassing a healthy cells is not something which is very much advisable, because we have these healthy cells available. Why not use them to get the maximum voltage possible from the converter? So, we want to use 5 healthy cells from A phase, 4 healthy cells from B phase and 3 healthy cells from C phase. Now, then but the pole voltages VAO, VBO, VCO will become definitely unbalanced. Okay. So, you can see here AO, BO and CO, these 3 phasors have become unbalanced here. So, if this become unbalanced, definitely the line voltages become unbalanced. Okay. And if the line voltages here become unbalanced, then unbalanced current will flow into the motor, which is not at all advisable and not recommended. So, what can we do? The strategy that we adopt is that if we change, so this diagram here you can see the unbalance is produced because the angle between AO, BO, CO is 120 degrees. But if we change the angle between them, okay, which is shown by this red color equilateral triangle, here you can see that AO, BO, CO, they are unequal, and the angle between them, that is the phase shift between the pole voltages AO, BO, CO, they are not 120 degree anymore, they are different angles. Okay. If you make those angles different from 120 degree, then it may be possible again to get back this equilateral triangle. The equilateral triangle corresponds to the balanced line voltages. So, it means that in spite of having unbalanced pole voltages, it is possible to get back balanced line voltages, which is shown by this red colored diagram. This is the balanced line voltages, and this is these are the 3 unbalanced pole voltages, and their magnitudes are different and their angle is no longer 120 degrees, it is a different angle. If we get a balanced line voltage, that means at this point here we get a balanced line voltage, then the motor will not see any difference, okay, because the motor will not even understand that there is a fault inside the converter, because the motor phase voltages will become balanced again. As soon as the line voltages become balanced, the motor phase voltage will also become balanced and balanced current will flow. So, the load will never understand that there has been a fault inside the converter, as long as we can ensure that the line voltages are balanced at the output of the converter. Now, when we do this, of course, you can see that there are 2 things happening. First is the balanced voltages produced during a fault condition, the balanced voltage produced has reduced in magnitude. Okay. So, you can see that earlier we were able to produce this much of length of the equilateral triangle, but now we are able to produce only a smaller magnitude equilateral triangle. So, that means the magnitude of voltage available to the load has reduced. Secondly, we also note that there is a potential difference now coming up between the point N and O. Okay. The point O is here and point N is the neutral point of the load or the motor. So, between these points N and O, this point and this point N and O, we will now see a potential difference coming up, and that is shown in the phasor diagram here, V N O. Okay. This is a common mode voltage, because this voltage is existing in all the phases, it is there. So, V A N plus O is V A O, V A N plus V N O is equal to V A O, and also V B N plus N O is equal to V B O, and V C N plus V N O is equal to V C O. So, which means this is a common mode voltage which is present in all the three phases, and this common mode voltage cannot allow a current to flow, because the points O and N are isolated from each other. Okay. But we are able to produce a balanced line voltages and of a lesser magnitude, and so the motor can be run with a lesser voltage magnitude. This is possible.